Hey everybody, this is Dark Guardsman. We're back with another video, so I'm going to really quickly kind of talk about and showcase one of the new features in atomic science, because it's not going to be obvious, it's not something you're going to see right away. It's more of a background element that I spent the last couple days working on and getting changed out. That way the system functions much nicer than the previous version. Now in the previous version, when it came to the thermal radiation, all that stuff system, we were using a separate map for each one of those systems. Each system would work on its own independently, would interact as needed. So like the radiation material map would affect the radiation map, which it still does. And then the thermal map would be affected by sources, which it still does work this way. The thing was that each of these maps each of these systems use their own map for data storage. And on top of this, each of them used an integer-based system to store data. Now this worked. This made sure that the system was incredibly low memory usage, which for those who didn't see the stream, we went over all the numbers and we found out, yeah, it used very little amount of memory. I actually can bring this up real quick just to show you guys the number and talk about it real quick, because I don't think we had a huge amount of people that were in the stream when I did this, and the people that were in the stream did not stay around very long, because I don't blame you guys. Even I get bored of the mathematics, and I was the one doing it. But yeah, we did the math, and this is kind of important. This is for any of those who are designing mods and are trying to design for the more long term, rather than just make something and get it done with. Designing is very useful, because it lets you go look at what you are doing, what already exists, and how you're going to implement it to achieve your goal, and then see how that would work before you even write a single line of code, which is really useful, not only to save you time when it comes to writing the code, but it also helps you learn about how your systems work together and adapt your designs a lot better. So for the memory usage thing, of course we got some data up here. I did some research on the memory size of a whole bunch of things. So you've got your standard data types here. Most people who are more on the, not so much the one-on-one side, starting to get to the junior developer side, should know these to some extent. If you don't, look them up. It's not that big deal. I have to look them up myself. That's the reason why I've got the table at the top. But some things people don't actually know. Objects have a header of 8 bytes. This is any object you ever make will have a header of 8 bytes. Not primitive types. Primitive types are, this is what they are. Arrays have a 12-byte default header, because they have the 8-byte header for the object, 4 bytes for the array size, as well. This is something that took me quite a bit of time during the stream to figure out. But arrays, when you build them, they will take up the primitive size, which is quite obvious. So you're going to be storing, if you're storing an array of 10, you're going to be using 10 worth of that primitive. So if you're using integer, you're going to end up with like 40 bytes of data. But the thing that wasn't so obvious is how do you determine the object size? This one is going to have 4 bytes for the pointer, which is going to tell you where that object is or what its ID is, so you know how to attach to it. And then the object size. So this is, it may seem obvious to some people, but it wasn't so obvious to me because I haven't actually looked into detail, at least recently. There's probably been a point in time when I've read over all this and I understood it at some point, and I just forgot it because I didn't use it. The other thing that was figured out that wasn't so obvious as well is that objects will pad to a multiple of 8. So if you end up, say, storing a byte or a boolean right here, and you have an object, so you have an object that have 8 header, and you have 1 boolean in it, you're using 9 bytes. Somebody will go, oh yeah, my object uses 9 bytes. It doesn't, it uses 16, because it has to pad out to a multiple of 8. So you end up having 7 bytes of unused data for your object. So it's kind of important to think about that when you are designing some data structures and stuff, because you can have a ton of wasted memory. We do have a bit in my design, so it's not that I'm not very good at designing a way around this as well. But our previous system, is I went through and I did all the data types for all of this, and I went through and made sure we had all the information ready and stuff. So I went and grabbed basically the system, the data map, the chunk, everything like that. So we labeled all that information out, so we have int, all that stuff, figured out what its size was. So we figured out that we're going to be using 4 bytes, etc. Per int. So yeah, we're going to have an array of like 10,024. Let me switch songs here because it's a worded song. Even though that song is actually a pretty good one. It's weird, but it's at least good. Okay. So yeah. 4 bytes per int. We have an array of 256 ints. So this is going to pre-size. It's going to be pre-used memory-wise. I actually do plan to maybe get some of this memory usage down, but I haven't figured out a good way to go about it. But this is like 1 kilobyte. It's not that big of a deal. So you've got all that data, all of it comes down to, eventually we end up using 10,056 per layer. Not that big of a deal, still down at about 1 kilobyte per layer. We can have up to 256 layers per chunk, which you'll never see. You'll never see a full chunk filled with any data type at all. You'll have to try really hard to achieve that. Even Minecraft doesn't achieve that most of the time. But you go down to a data chunk, whole bunch of information. So 1056 with padding. I think we ended up doing this the first time, and I ended up getting the math wrong. This is the reason I had to go look up the array, because I was like, oh yeah, if I have no data stored in this array right here, then theoretically I'm not using any memory. I was wrong on that. You're using the pointer memory. So if you actually sit here and do this, so just this sitting empty, it uses 1 kilobyte. Nothing stored in it. No information, no integer data, no layers. It uses 1 kilobyte just to exist. Then when you start actually considering what's going on with it, if we have a full chunk, we use 271 kilobytes for a full chunk. We've a layer of 10, so just like 10 layers being used, which is what I expect most people to be using, 12 kilobytes. If you have 100 chunks that are completely full, 27 megabytes. So that would be like per player, because most players are not going to be right next to each other. And then if you had 100, so you'd be 1 megabyte. So that's not a lot of memory. That's really low. This is kind of what I intentionally designed this system. I designed the system to have a really low memory usage, really low memory churn, all that kind of stuff. And here's the original data I did when I was designing the system. I went through, and it's roughly the same. This one doesn't account for the padding, doesn't account for a lot of the other stuff, but it gets really, really close to the system that we had in mind. As you can come down here, you can look at this one, which was, I believe, a full chunk. No, that's full chunks right here. So 262 is really close to 271. So that was really, really close, almost on the spot when I originally did this. And I believe I made this like several months ago, because I designed the system a long time ago. Now we went to go design the new system. So the new system is not as memory efficient, but what it is designed to do is solve quite a few different problems. So when we use these reactors here, and when you actually put rods in them and stuff, the ideal is that when you take a rod out, it's supposed to stop doing stuff. When you put a rod in, it's supposed to do stuff and turn back on. There's a bit of a delay with this because of some chunk sinking and stuff. I still have more work to do on it. But when you put a rod in, it starts. Pull a rod out when it goes out. What was happening with the original system is if certain events didn't fire or synchronize just right, just like you saw with that first thing, you would get a situation where things would not clear out. And it had to do with that integer-based map system. So with the integer-based map system, how we were doing things is that when this was populated, we would do all of our mathematics, and we would then dump that data into the system. And then when we pull the rod out, we would do the mathematics again, and then pull the data out of the map. So you're basically doing a subtraction run to take stuff out, an addition run to put stuff in. This was cool and simple, and it worked. The problem is what happens when the area around the reactor changes. If I start breaking blocks, I start placing blocks, I start changing things, that mathematics no longer works properly, and you started getting spots that retained heat or retained radiation when they weren't supposed to. You also ran into issues that what if the math didn't run correctly, even though all the stuff was still relatively the same because some other property of the system changed. You would get the math that wouldn't run right again, and then you would not get the data pulled on and off. This was problematic, as it made it really hard to fix problems. It resulted in me having to dump the data every 5 minutes and reset everything from scratch. I didn't want to do that. You also ran into issues that if we needed to update the data quickly or we needed to clean up quickly, we had to run a whole bunch of calculations. So if I wanted to destroy all the data, I would have to recalculate a very complicated pathfinder or recalculate a very complicated ray trace just to remove data. That was problematic. So we switched over to a new system just so we can remove data quickly, and we can modify that data. So say if I wanted a slow radiation decay as the reactor turned off, I can now achieve that goal by having it just go through and track all of this data. So this new system we ended up switching over to, because I'm kind of trying to dodge saying it right away. We switched over to a node-based system. So previously we were using an integer to represent each data, now we're using nodes to represent each data. Now during the stream, I figured out that this is going to use a lot of memory. But I found the way we're going to get around it. I found the way we're going to get around the issue, and I got to make sure I do different music next time because that's got a lot of spoken word songs in it. But the way to get around this issue of using a lot of memory is instead of doing a map per data type, we use a single map. This removes a lot of the overhead because instead of having to create a new map, which would have a huge amount of overhead, and we were kind of figuring this out down here, so I don't see where we're at. So for the most part, the new system uses the same amount of memory as the old system, except when you come down to the layer is switched over to an array of array list, which is confusing to say, but you have an array list per block on that layer. You have 256 blocks per layer. This ends up introducing an additional Okay, so if it's empty, so if there's nothing stored in here, it uses the same exact. So if it as an empty data list, it stays the same. But as soon as we start introducing data points in here, it's going to get 64 bytes per new array list created. This has to do with the overhead of an array list, plus the fact array list pre-sized with 10 values. So if we ended up doing a completely filled layer, we end up introducing another 16,000 something bytes just by having the array list, no data stored. Then as we end up introducing more and more data, we end up having more and more data usage, which goes out of hand. So for a full chunk, we end up introducing 14 more megabytes per chunk if it's full. This is problematic. So we ended up going with a system where now we have one map that tracks all of our data. And the trick we get around how to make this work is that we have the nodes. The nodes track what type they are. So they go, hey, I'm a thermal node, I'm a radiation node, I'm a radioactive material node, I'm whatever you want to stick on the map. They all stick in the same slot type. So when we start looking at this 14 megabytes, you have to keep in mind that the previous version up here was using, I believe, 1 megabyte. Oh yeah, it was using 270k. So yeah, I can't really compare this. But it was using a ton of data for 3 different maps. So now we've got one map. We've got a node-based system. Node-based system can be expanded and contracted. So this 14 megabytes, to be honest, is not that big of a deal when you now realize that we can store a massive amount of information in that 14 megabytes. So instead of just being able to store an integer, I can store floats, I can store doubles, I can store longs, I can store objects, I can store whatever I want in those nodes, because those nodes are only just a location-based system. So we can track anything. We can track gases, we can track fluids, we can track some spatial particle, whatever. We're probably going to use this for the particle accelerator is how it's going to actually end up working. We can do a ton of data segment here, and all we have to do is just go to the map, hey, I want all my thermal nodes out here, and I want you to calculate the value, which then produces this result here. And the memory usage isn't actually that high, because you got to keep in mind, it's a full chunk, you're never going to see a full chunk. So let's actually go back to the data here. So I think what we're going to end up seeing, so it's 57 kilobytes per layer. As I said, I expect only to be like 10, 20 layers to be used in the system at this point. So it's going to be 10 layers of radiation. If it's going to be thermal, it's going to be a lot more, but it doesn't really matter because you're going to end up using probably a bit of these. So say we had like 30 layers per chunk, you're going to be using a megabyte to 2 megabytes per chunk, roughly. That's not that big of a deal when you think about it. The reactors have a max range of 50, and usually they're stopped by walls, so you're probably not going to see even that much data even being used by a reactor. It's really only going to be when you start doing things like setting off nuclear bombs and stuff, and you spread radiation around. When it starts to get the memory usage, will start to get up in a certain range, but we're going to be having systems to auto-decay off of that. But yeah, that's kind of the system. I probably should have put some pictures on screen and talked about kind of how it works. We can show the code though, so I'll kind of show how the code works for some part. And there's like tons of stuff in here. So we have radiation nodes. The nodes are really, really simple. They just store the source. They store a value. We use a flywheel pattern to recycle this. So you have that memory usage that is there. You should have less memory turnover. This storage ends up using like a megabyte or 2 of data just to sit around. I don't think it's even that. I think it's a lot lower. Because this class right here is 8. This is like 16, so 16 times 400,000. Yeah, so it's a bit of memory. I am going to make this configurable so you can control how much memory usage, but 6 megabytes to have a flywheel pattern. This will probably never actually be full if you're running a single player. If you're doing single player stuff, this will very likely not have anything in it, simply because you don't really have a lot of stuff kind of working in that way. And I believe, yeah, it's using a concurrent link queue, so to be honest, until the data gets completely full, you won't see that. This will auto-expand and contract as needed, so you'll have a very low memory footprint of this. It's just that it can max out at 6.4. There's several of these that sit around here, so we can reduce the amount of memory churn. Memory churn is basically when you're producing an object, and then it dies. So you use it, you produce it, you stop using it, it sits in memory, the garbage collector has to come through and clean it up. That's what you end up seeing. Memory churn is becoming a problem when you get a ton of objects being created, and the garbage collector has to work really, really hard to do stuff, which then causes CPU issues, which then causes tick rate to go down. So this is here to kind of prevent CPU problems. This is what this is for. There's a version for that. There's a thermal node, looks exactly the same, very simplistic. It gets a little bit more complicated when you start seeing like things like the thermal sources, because we have a map node system. The reason why I wanted to go to the system is we can now track the exact position data of what each source affects. So I can see what sources of effects. I can then take this information while sitting in my reactor. I can go over all of my nodes. I can slowly decay them down. I can increase them in power so we have like nice scaled up power designs. I can have this effect in other reactors. If we have a system where the more radiation you're producing, the stronger reactors get, we can have a system like this that can actually detect that and actually work with that. We can do a very basic system, but we can do it down here. We can disconnect data from the map, so we can go, hey, I want you to disconnect from the map. I want you to connect to the map. I want you to clear all of your data. We can call this stuff and have all of this clear from the map without having to go through and do a whole bunch of mathematics. So very fast on the CPU time to get everything pulled off and on, which was an issue previously, is that if you had a lot of reactors running and you were turning them on and off, is that you could get a problem where it would take upwards of a minute for the math to run in the old version. This version, this is almost instantaneous. See, if I pull this rod out, that reactor turned off. You are literally seeing the time it takes, which is slightly illusionary, is that those bubbles you're seeing, those are particle effects. Those take time to decay. But when we stick stuff in, it's almost instantaneous. That was not possible in the previous version. It's much, much faster at doing its startup time and its decrease time with this new system, because it can populate the data much quicker, it can put it in the map much quicker, it can handle stuff. We've also solved a lot of the concurrency problems too with the new system, though that had to do with us switching over to doing letting the server take off our additions and everything else, which we'll show in the rad exposure thread. So we now use this right here, which I'm going to convert to a method or class or something, make it look a little cleaner. But we only have to run the Pathfinder once, which cuts our amount of usage in half, because you had some pretty serious usage in order to get everything, so it's half the runtime. It now runs very fast. It recycles as much data as possible, so when it's changing values, so say for example you were going for 300 to 400 radiation from a reactor, it will take the original data that it had stored, it will recycle that data so you have even less memory usage, put it back into the map, and reuse it again to ensure that it's not wasting as much resources as it did before. There's also a ton of safety features that we're going to be implementing to the system, so that way if for some reason the reactor got destroyed before it could clear its data, the data will automatically devalidate and then something will come in and clear it out. When it is devalidated, it no longer counts to the map. So when this reactor gets destroyed, the data is gone. And not because it was actually cleared from the map, because it's still probably in there. Although the reactor does have a devalidate, so likely it did be removed. But say something removed it without devalidating it. Say like deleted the tile, some kind of corruption happened. The data will say it's no longer valid, and will then, anytime something tries to check against it, will go, hey, how much thermal energy do I have in this position? How much radioactive energy do I have in this position? It will say you have none, because it'll go to the node and it'll go, hey, what are you worth, node? And the node will go, I'm worth nothing because I have no source to actually attach to. And if you put the reactor down there, it'll work just fine. And let me go pull that rod out of there and duplicate it. Works perfectly. So we go down there. That's basically the stuff. Thread runs. Each source will control its own node set, both for the radiation and for the thermal. The radioactive material does not really have this type of system because there's no such thing as being able to produce radioactive material. Radioactive material exists as an object in the world, so that system is going to need some more work. I have disabled it temporarily until we can actually get all the systems in place and working 100% efficiently. But some of the other aspects here, so you showed all that. So the data side, which I think I've showed off kind of how this works. So we have a data map. The map actually controls tracking all of the chunks. We do it very similar to how Minecraft does it. We keep track of a long representing the chunk's position to a chunk. We keep track of loaded chunks. We unload stuff as Minecraft unloads. We do keep a cache of stuff waiting to be unloaded, so that way we can slowly unload it just in case there's orphan chunk loading or there's some kind of issue going on where chunks are being loaded and unloaded, loaded and unloaded again. That way you don't have a ton of memory turnover and CPU wasting time as stuff loading and unloading from disk and everything else. So that is handled that way. We have tons of methods to handle everything. It's actually well documented. But here's where the part starts to come in here. So we get an array list of nodes. So we actually store all of our stuff as a data node. The data nodes are very generic, so if somebody wants to come in here and implement their own system for this, end up adding some kind of system to Atomic Science, they are more than welcome to, though you will need to actually add your own entry to the enum, which you guys can pull request if you need to. So if you wanted to come in here and add an O2 system, if you wanted to come in here and add some kind of gas system, some kind of pollution system, you're more than welcome. It's very likely I'm probably going to pull this data system out and use it in other mods because it is very nice. I'll have to look at how to make the API function in such a way that we're not ending up with like 3 or 4 different maps. We still only have that one map because that's the concept behind it. In order to make that efficient, one map needs to be used, not 1,000. Add data. Tons of event fires. Every time data is changed, there's an event being fired off to say, hey, data has changed. Very useful so you guys can catch this event. So if you want to end up implementing machines that depend on the thermal or depend on the radiation, there are ways to detect for it. Remove data. Remove data does the same thing. It does a fire event change as well. These are separate events, but they do have a single parent, so you can just capture for the parent if you just want the data change. But if you're looking for node additions or removal, those are separately fired. That way, if I, for example, go to add a node, you can then actually change that node. You're more than welcome to change out with an own node. So if you have a more efficient system you want to use, or you want to change the behavior of the nodes, you want to do more manipulation, you could do that. When the node is changed, it also does change the new value as well. So that's in there. When this actually does get populated, the system that actually populates the stuff in here is pretty straightforward. You've got the layer system did not change between the previous version, but the internal did change. So you have an array list up here. The array list is not actually populated until you actually go to put something in the map, and eventually we'll end up deleting the array list at some point as well. We'll probably have some kind of timer going like, hey, this hasn't been used in a while, let's go ahead and clean it up. That way we can reduce the overhead memory, so we'll have our own version of garbage collection going. But when you go to add it, creates the relay list, adds the data to it, updates the blocks used, which hopefully the remove code reduces the blocks used. I'll have to check that later. But it does do that, it does handle all that information. All that works pretty straightforward. When it needs to get values from everything, you kind of saw that slightly in the... Yeah, we'll go this way. So data map. So we do use lambda expressions to kind of handle the additional stuff. So when we have a node here, we can go and get the value of something, pass the array list in here. So we can have an array list, and this doesn't even have to be from the map. If you want to test your own stuff, maybe you have some kind of your own system that's controlling and related to nodes, you can pop it in here and it'll do the addition for everything right here. Pretty easy. When people add new data types here, all they have to do is add a new reference here. We have interfaces for all the nodes as well. This is mainly just so we can get to the data. I didn't want to force the nodes to have a particular data type in case you want to come in here later and say we want to put a float here for the radiation material value, or we want to say the thermals can have precision in them. We can actually do that now because we're no longer stuck with an integer-based system. So there's a lot of ability that these nodes can now have. Although we do still need to implement a save system for this one right here. I removed the old save system until we can get it actually implemented again. That's the most of that. Everything's kind of working. These reactors can be turned on, turned off. You could probably put more rods in here if you really wanted to. Get a much higher degree. The steam turbines don't have animations still yet, but they do produce power all the same, so the system is fully functional. I have tested it. I will be testing server-side functionality here later after this video and doing more tweaking and working to get it stable for 1.12. But this is playable. This version that actually has a new system is up on Curse already. If you guys want to go ahead and download it and toy around with it and see if you can find some way to break it. But until then, I'll see you all later.